Okay. Yeah, this the 7th week. It is according to the plan that we are going to discuss about the topic of problem complexity and several type of solution approach that commonly available for optimization techniques. So there are there is how many this four. I divide the contents into four parts. First, basically it's two big parts: the complexity analysis part and then the solution approach part. Okay, for the complexity, it consists of three sub part, in which we will discuss about complexity analysis in general, and then we move to a measurement of complexity. Okay, this measurement normally studied in computer science, when people in computer science normally develop algorithms, and then they want to know is this algorithms how to measure the performance of these algorithms, something like that, right? It's like when you measure something, you need to have a unit of measurement, right? And to measure how your algorithm performance, then you need to have the measure of the unit of those measure. And there is a notation being introduced to measure that one. It is very common. It's called big O notation. Later, I will not really in depth about how do you calculate the big O, how do you really come up with those notation, but I will give you the ideas so that you can explore independently by yourself. Perhaps I think that's more effective, since when I study graduate studies also, I did the same thing. At first, I learned how to calculate it during my undergrads, but it's not really complete. But I start to understood more clear after. For me, the case is that my reviewer, when I submit the journal, they ask me how about the complexity of your algorithms that you propose? How good is it? And then what is the complexity? Is it linear? Is it exponential? Is it factorial? Something like that. Give me the big O notation, something like that. So that's why I start to explore that, and I try to deliver this to you so that you will have at least the basic knowledge, so that when you explore by yourself, you will not really lost about that. Okay, so second one, big O notation. Then okay, big O notation is to measure normally for the algorithm complexity. So when we talk about optimization, we have two sides. First is the problem itself. Okay, and then the second one is the algorithms. When you want to solve a problems, there is okay, problems have its own complexity theory. Okay, so they have their own complexity category. So, and then how do you measure those? How complex is this problem? Okay, we have another category for that. We call it problem complexity. But in order to decide whether your problem is complex or not, you need to understand the algorithms being developed to solve that problem. Okay, it's like this: when you have a problem, and you have a method, a method to solve that problem easily, so you will not say that problem is complex, right? But if you have a problem, and then even though it looks simple, but later on when you try, you propose an algorithms, seems like your algorithm cannot solve the problem quite easily, then your problem become complex problem, because even though it looks simple, because there is no algorithms able to solve that one easily, right? So that's why I introduced the first one. The big O notation is for measure the algorithm complexity, and then after that, based on this algorithm complexity, we can categorize whether this problem is complex or not. Okay, so that's the relationship. And then based on our knowledge about complexity of the problem, why we need to learn this one anyway, something like that, right? It is because when you understood your problem, you will really know, at least you have idea what kind of tools you should use for solving this problem. Okay, yeah, it doesn't make sense if you have a simple problem. Simple means it's not complex. Then you use very sophisticated tools and very much effort to develop the algorithms that is very complex to solve those simple problems. It's useless. It's like when you it's like using a bazooka to shoot a mouse, something like that. Yeah, I mean, like it's overkill. So the knowledge about problem complexity will help you to will guide you and help you to decide what type of solutions that is suitable for your problems. Okay, so that's why I just put it solution method at the end of the course, at the end of the class today. But again, implementing this solution method is not going to be easy because several optimization problems, we already learned about it. First, like when we previously, we already learned mathematical modeling, mathematical programming. And inside of those mathematical modeling and programming, we have exact solution that is called by the solver, like branch and bound, branch and price, all is embedded inside the solver of the mathematical programming. But the things that you don't learn yet is a solution method that is not belong to those categories. Okay, later I will discuss what is the advantage, what is the disadvantage, and then you can use that information to decide or which solution is suitable for your problems. Okay, it's quite long because I think you should have a grasp about what we are going to discuss, so that you will, how to say, try to keep yourself on focus during this class, because I think it's quite important for today's class. Okay. Okay, this one, just a course outcome. You can read. We have two course outcome today. Okay. Before I start, perhaps I will ask you, when you okay, this in general, okay, how do you decide whether this problem is complex or not? How do you decide whether, okay, I think this problem is difficult to solve, or I think this problem is complex? In general, how do you, even a problem in your life also fine. What do you think about that? Anyone can help me give some how to say, thought about that? How do you decide a problem is complex based on your own thinking? Anyone tuning in? Perhaps just random thought that first come up on your mind. Chat is also fine.
If there are too many stakeholders, sir.
It's too many stakeholders. Difficult to decide, right? Difficult to make decision, make the problem complex. Can I say it like that? When you have many stakeholders, many people will give you many constraints, many opinions.
Yes, sir.
And then it makes you, as a decision maker, this problem is complex, difficult to decide, difficult to make the best decision, right? It's complex. Okay. That's how to say, in general, is very good, true. But when we now what we learn in our course, advanced optimization technique 1, is more to if you flashback to the first first lecturer that when we discuss what will be discussed in this class, is actually more to a simplified problem, right? When you have problems, there is many stakeholder, many uncertainty being involved. For the tools that we are discussing in Advanced Optimization Technique 1 is most likely will be, first we will need to simplify those problems so that there is not as many as noise available for us to help the decision maker to decide what they are going to do. Okay, so those idea from Jeremy is good, but it will be discussed more on the Advanced Optimization Technique 2, in which you will have many uncertainty being involved. Perhaps you will use simulation techniques, and those are topics for another discussion. Okay, but now let me give you more specific about the complexity analysis that we are using for that we are going to discuss for today. Okay, if you already have ability or you can judge how to simplify the problem, then actually to make the decision, it is the matter of we in AOT, Advanced Optimization Technique 1, when you make the decision or the variable mostly become a deterministic variable in which you can have a good approximation about those parameters or uncertain value, it means that actually you already simplified the problem a little bit. But if already simplified, why you still consider it difficult? Okay, so this is another layer of those questions. So the first layer, I think Jeremy answered it very, very good. But later on, okay, if you cannot make decision, too many noise, too many uncertain, simplify it. Okay, make it become deterministic, make it become a problem that is easy to digest in terms of computational stuff, something like that. After you simplify, why do you still saying this problem is difficult? For example, last meeting we talked about TSP and VRP. The TSP and VRP that we discussed, it's far from the practical issue that is being addressed in the field. For example, in the field we have uncertain travel time, yeah, uncertain travel time, uncertain demand. Sometimes also the customer also have priority, and like you said, the customer also the stakeholder, then they want one to deliver earlier, one want to deliver a little bit at about this time, something like that. Those are practical issue, but we don't treat that one as that level of detail in the VRP or TSP that we discussed last week, right? It's already being simplified. But why VRP and TSP still considered to be complex problem? Okay. Now, okay. Then here we go to the slide that you can see when you for those type of problem, when you already simplified it, but why do you still consider that as a complex problem? Perhaps it will base on the algorithms. Okay, when you have those problems, okay, deterministic type of problems, and then now you want to solve that problems, you will use some methods, right? This method normally implemented in an algorithms, and a step-by-step approach to solve problems. Okay, algorithms. Then when your algorithms, the algorithms that you are going to use to solve the problems, that can be used as an indicator whether your problem is complex or not. Okay. For example, of course, the first thing is your algorithm able to solve the problem until it gets the optimal value or not? That one, number one. Okay. If the algorithm is able to solve the problem until get the optimal, ensure the optimality, most likely those problem is not complex. Okay, that's one thing you need to grasp from this last. When your algorithm can solve the problem until optimality, then it is tend to be not a complex problem. But wait, yes, it is able to solve it until optimality, but the time it takes so long, okay, like TSP, like if you later you will also see again, there is algorithm like branch and bound, branch and price that is embedded in the solver, exact solution approach, or like column generation, right? Labeling algorithm, something like that. All is about exact algorithm. It is able to solve the TSP until optimality. For some TSP, not for all variants. But the time it takes will be taking so long. It is even for small number of problem size. For example, you have more than 15 cities of TSP or more than 20 cities. The time it takes to solve the problem using exact solver will be like grow exponentially. Like let's say in 10 for 10 nodes, you can solve it like, okay, 3 minutes, 5 minutes. But when you rise up, become 15 or 20, it become 5 hours, 6 hours, then more than that become like unsolvable, like too long. Even your computer sometimes out of memory to find all the specificity for the solution. Then we can say that the computational time take part to determine whether your problem is complex or not. This one we still talk about the algorithms, okay, in the perspective of the algorithms. Okay, but when you explore more or analyze again in detail, computational time, it is a relative things actually. Relative to what? First, relative to the instance that you are going to solve. Okay, like VRP. Okay, if you solve maybe the same amount of instance, 15 instance, and then the other also 15 instance, 15 nodes. Instance number 1 have 15 nodes. Instance number 2 have 15 nodes. But the network of or the demography of those nodes, one is more let's say, I'm not sure, but maybe one is more randomized. The other one is more clustered. We don't know actually which one is easier to solve, but let's say assume that the clustered is easier to solve. So we cannot say that for 15 nodes, TSP is always complex. We cannot say also, because when your instance is easy to solve, then it doesn't show from the computational time. Because let's say it's cluster, it's like really in the close place, close together, so easy to make the routes. So the computational time will be fast for that type of particular instance. Okay, that one thing. Another thing is the machine that you are using. Machine means the computer, it depends. Algorithms sometimes applied in the CPU, sometimes applied in the now graphical processing unit have also powerful computation. So it really depends. Even one computer with the same brand, let's say using Intel CPU, but with different series will give you different computational time. So it is not wise to compare computational time of your algorithms. Moreover, if you run it in the different machine, okay, there is a way to do that, but it's more advanced topic. You can see in the paper later. But for in general, we will not compare the computational time of one algorithms with another algorithms. Moreover, they are running in the different machine. Okay, so be careful with that. If you are doing research about optimization and you are developing algorithms, be careful when you are reporting the computational time. Don't make silly comparisons. You say that your algorithms better because the computational time is better from the other one, but you don't check the machine that you are using. That's it's not wise. Okay. And then, well, it's actually applied also for machine learning, artificial intelligence type of research, because it involves computational. Okay. Be careful with those comparisons. And then, so in general, we can say that the result of your algorithms, in terms of computational time, when you earlier we said that computational time represent the complexity, is not easy to be how to say, accepted in general. Computational time cannot be accepted easily to be a measure for complexity analysis for your algorithms. Okay. Because it really depends who implemented, how they code it. It's different things, the data set, the computer, and things. Okay. And oh, sorry, this reference is from, it's not from HCI actually. This one from Daskin books, the one that about network design. Okay, so what should we do? Okay, but if we cannot use the computational time. Okay, so that's why people that develop algorithms, people that develop this type of algorithm, it is already commonly known that we have a theory, okay, that can accommodate the type of problems, the type of algorithms that can also predict the computational times, okay, and the storage of requirement, because computing power needs storage in your machine to solve the problem. So we have a theory about that. Okay, what is that theory? That theory is normally denoted as complexity theory. So it's how to say, it's how do you define the complexity of your algorithms. It will be discussed in this theory. Okay, and most of the theory, yeah, complexity theory is focused on the worst case of the performance of your algorithms. For example, earlier that I mentioned that perhaps for 15 instance, if the complexity, if the demography of the instance in the TSP is easier to solve than the other 15 instance, then it's not be able to be used for comparison. Okay, but complexity theory can go beyond that, so that when you consider 15 nodes, we will always be able to see the worst case scenario for these 15 nodes. Okay, the easier way I can say is that, for example, if you have, let's say, make it smaller, okay, 3 nodes for TSP, 3 nodes, actually you have only, there is how many, 3, 2, 1, 2, 3, 1, okay, 2, 3 factorial, right? 3, 2, yeah, 3 factorial to decide to how many combination of the sequence of the city visitation, right? That is the one that you use to measure the complexity, not the time, but the how many steps, how many possible solution need to be explored. Those are the things that you use to measure complexity theory. Okay, that's just one small part of the discussion. Okay, but okay, because I talk about a lot about TSP, maybe it is interesting to have a little bit how to say, intermezzo, that actually this game is quite popular in 2015 when they first launched. I think almost all around the world people are crazy to play this game. but now I think the popularity is already declined. But still, some people play it, including me. I think, and now I will let you see there is something interesting about this game. And even though it's just a game, some people study it immensely, and even several papers published about this one. I also quite surprised, and it is related to what we are going to discuss, or what we already discussed earlier, like they model it using TSP problem and stuff. Okay, so that's why before we discuss about it, I want to let you see, if you not yet not a fans of the game, I want you to see how the games are being played, and then so that you can have like foundation for the discussion. Okay, but because this is from YouTube, I will need to pause the recording first. Okay. Yes. Okay, so actually, yeah, 2015, I remember I'm doing my PhD at that time. So yeah, sometimes, yeah, when you do the research about optimization, sometimes you have more time waiting for the result to come out. Like when you run your algorithms, when it doesn't run good, you try another tweak, another modified a little bit, and then you run again for so long time, like 1 or 2 hours. Then normally in our lab we decide to go out and play. And at that time the Pokemon is not many. Even how to say, at that time I remember there is one Pokemon, that the fat one, the one that in the video, so the Snorlax. Nah, that one, when it's appear, everyone running chase that place to just to catch that particular Pokemon, like crazy, like a crazy crowd there. So I think it was fun, but now it's already, yeah, because most people consider it's dangerous as also. But now the popularity is not as much as last time. But anyway, this is what I want to talk to you. It's just I don't know. This one is in Canada, Waterloo, Canada. So they have a research specifically designed. Let's say Pokemon. They have something called Pokestop, right? It's like a place that you can go. So this is like a mixed reality and augmented reality games, right? It means that you need to explore the real world, and then so that you can have some achievement that you can get in the games. So it's like mixed between digital and then the real world that we have. Like, yeah, just like they want to do with the Pokemon. And we have something called Pokestop. Pokestop is the place that you can visit to refill items. Like, for example, whenever your Pokemon need some fruit to give to make them happy, you can get it there, or you can find many useful items that you can use for your games, something like that. So you need to spin those Pokestop, but you have to in some approximate distance for those locations. So normally people will walk around to find those Pokestop, and this research is quite fun. I think they map all the location of the Pokestop in their area. Let's say this one, Waterloo. Maybe this is near the university, I guess. And then they want to know what is the optimal way to visit all those Pokestop within a day. I think it's quite funny. Then it become a research. It's legit research. And if we think about it again, that's research really TSP with some modification, of course. For example, you can only visit one. You need to have the range, something like that, and all this. But the basic is implied. The basic of TSP. And I think now, I don't know, that last time, this is, I checked last 2016 or 17. is because it's still getting popularity. I think they already try to, or already published, perhaps you can find it. I'm not sure, but at least this is a fun research, I guess. And it apply what we are studied in optimization techniques. Exactly, TSP, if from my perspective. Okay, why this research is challenging in okay, in terms of fun, okay lah. They make it interesting. They make the game interesting. But in terms of complexity, this is also interesting. Okay, for TSP problem, like I mentioned earlier, if you want to solve TSP problems, here they give the explanation, the approximation. Okay, let's say if you have only two Pokestop, your option is actually visit the first one and then visit the second one and then go back, or visit the second one first and then visit the first one and then go back. That's your only option. It's easy, right? But if you go through in more detail, okay, increase those number of stop, number of n. Okay, what can you see? Okay, look, if you look the table here, the number of n increase even just slightly. Okay, just see this, the small increment first. 2 to 3, the increment become twice, triple as much. Okay, triple. Okay, from 3 to 4, okay, I expect it, if it is a linear problems, so it will be triple again, right? Okay, so 3 to 4 is okay, triple. And then from I think this one more than triple, four times. And then 4 to 5, you see, the number is growing. 24 become 5 more times. And then here 6 more times. And then suddenly if you jump here, you see the difference. This one only three number here. Here, how many number is this one? I cannot even read it if they don't put comma here. Okay. Now, 14 is considerably small, right? If you see here from the map, 14 is just like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14. It's not even a half of the all the number of stop. Perhaps this one, perhaps, I'm not sure, but if this one raised to 100, okay, you can see here the approximation of number of possible route that you need to explore. You need the combination that you need to explore. So many, right? That's why, okay, this approach, okay, if we go about we talk about the complexity theory, this type of approach also being considered how to measure the complexity of the problems. Okay, now other than that, okay, that one is about the problem. Now about the algorithms, if you go back to discuss about VRP algorithm or TSP algorithms, the complexity of TSP algorithms for the exact solutions, okay, normally this big O notation, okay, let me go back first. The big O notations is commonly discussed in computer science fields. It's a notations that is used to classify algorithms. Classify. So it means that when you have algorithms, you need to find or to calculate or to measure the complexity. Then you come up with this type of notation, ON square, ON to the power of 3, ON to the power of n, or e to the power of n. This one, there is a way to measure it. It depends on your algorithm, the step-by-step that you use. And then based on this n, what is this n means? N represent the size of the problems. For example, for the previous TSP, n will be belong to the number of stop or number of city to be visited. Or if you are working on scheduling problem, the n is perhaps the number of job that you need to be scheduled, something like that. Okay, and this one, okay, after you come up with this for your algorithm, this one will be used to categorize how complex is your algorithms. Okay, because the solution, the computational time of your solution, like this one, this one will be time, the approximation of the time will grow accordingly with your complexity notation. So you just need to give them this one, and then you can approximate the computational time based on the notation, big O notation that you give to people that want to explore your algorithm. And then in more detail, here is the table. There are several categories. Previously, we said category to categorize the algorithms. Okay, algorithms based on their complexity notations, we will have, this is the general categorized. For example, constant, okay, O1. It means that whatever your price, the size of your problem, your algorithms will always use constant time to give you result. That is constant type of algorithms. Of course, if you have this type of algorithm and it's able to solve until optimality, that is very good. But it's rarely happen. I don't think it's even happen for this. For a complex problem, you will not find this type of notation for your algorithms. Okay, a complex problem. Okay, linear is not complex. Logarithmic, I think, still okay, still not complex. The one that start to be considered complex or mildly complex, like quadratic, polynomial is not, exponential is complex, okay, and then factorial, of course, complex. This one is the one that you see in VRP and TSP, and then yeah, that one. Exponential also complex, okay. Okay, this one go up here is still considerably okay, easy, but it depends also. Some algorithm have this type of complexity. So some problem algorithm will have this type of complexity, and then when the number is growing, perhaps they can also move like this. That's also possible. But yeah, this one just for your information, because I also not really clear on the detail about that. But there is a way to calculate for your algorithms how to come up with this notation. Okay. Then when we talk about big O notations, we already know that later, okay, I have this type of algorithms. For example, for shortest path problems, we studied earlier, we discussed about Dijkstra algorithms or A-star algorithms. Those type of algorithms ensure, or if you find the big O notation, those type of algorithm will be giving you a notation that belong to either logarithmics or polynomial, something like that. It means what? It means that the algorithms, despite the growing number of problem size, will always be able to guarantee you the computational time for finding the best solution or the optimal solution for that particular problem will still be reasonable. What does it mean? For example, in previous example, I give you TSP, right? TSP, when the problem size is about more than 100, it's unreasonable already. It will take centuries to try all those possibilities. And then if you want to make sure it's optimal, it's so difficult. Okay, that's why TSP, VRP is NP-hard problem. But for a shortest path, it's different case. Okay, for example, Dijkstra. if you have 100 points to be considered, and then you shortest path is to find the shortest path or the shortest routes from one point, from origin point to a destination point. Okay, it's commonly applied on the map, finding the shortest routes from one point to another point in a map, right? For example, Google Maps, or even map in gaming. When you play a RPG, those also applied. These algorithms ensure you that even though the map is quite large, and then the location being the branches being considered in those is quite large, your algorithm, that Dijkstra algorithms, can ensure you the time to find those results will be still reasonable, not like VRP or TSP that it will take so many and so long time. Okay, that's why that is shown from the big O notation of those algorithms. That's why it's belong to shortest path problems. Okay, and then we have in between this one. Those are the two polarization, right? The one that is easy or not complex, commonly categorized as P, or polynomial type of problems. And the one that is difficult is, or mildly or medium to hard difficulties is normally categorized as NP, or non-polynomial. P and NP represent the normally big O notation of the algorithms being used to solve that problem. Okay, so Dijkstra is belong to P. The notation, if you check, it will belong to category of polynomial time. And then, for example, if you have algorithm for vertex covering problems, or VRP, the one that want to find the exact solution, for example, branch and bound, branch and price, the one that normally applied in the solver, it will belong to NP. Okay, so those are the two polarization. And then why there is NP complete, there is NP hard. Okay, NP complete. NP complete, it means that for some problem size, or for some category, for some condition, sometimes the algorithms can solve it in polynomial time. Okay, so that's why it has the intersection between the NP there below there. So it's for some case it is easier to solve compared to the NP hard. For NP hard, normally there is no available or proven algorithms that is able to solve it until optimality for even for a special cases. Okay, that's why it's belong to NP hard. Okay, I hope this can give you a little bit of introduction about problem complexity. Next, this one is the last slide, I guess, for the problem complexity. Yeah, first, why do we need to study problem or complexity theory? Okay, this is because it's summary. First is the to help you categorize, okay, categorize the problems, to help you when you want to find a solution for your problem. You need to know your problem better. If you're able to categorize the problems, it means that you have more information, and then you can apply an appropriate solution or appropriate solution approach that you can choose to solve the problem efficiently. Okay, and you will avoid that one that cannot solve it efficiently. Okay, and problem that can be solved efficiently using polynomial time, it means what? It means it belongs to P problem, okay, polynomial problem, like the one that I mentioned earlier, shortest path problem, P problems. There is, if that one is exists, then it is better you use those algorithms instead of the more difficult algorithms. Okay. Okay, a polynomial time algorithms. The algorithms that is used to solve this type of problems, that is proven to be able to solve that problem, like Dijkstra, is normally called polynomial time algorithms, and it's we can use those to approximate the worst case execution time as well for the problem size that we have. For example, if your Dijkstra, I'm not sure, I forgot the formula of Dijkstra, what O something, log something, or yeah, let's assume that it is n. Yeah, this is of course not correct. Let's say n is the approximation, and then you run this algorithm in a computer that you specified. Okay, this is my PC1, and then this is your complexity, your algorithm complexity. And PC1 with the number of n equal to 10, you get, okay, it is only 0.1 second. Okay, so when you have in how to say, the same one, PC1 with n equal 1000, you don't have to run it actually. You can approximate using this one. 100 times 10 to 100 is 100 times, right? 100 times of 1.1, 0.1 second is 10 seconds. So you can approximate this one will be 10 seconds, roughly 10 seconds. That's the beauty of having complexity theory or big O notation for your algorithms. You can approximate before you run it. Okay. But for the one that we discussed, location problem, we heavily discuss on location problem, location decision problem. For example, covering problem, maximum demand allocation problem, and P median problems, or even VRP also belong to location problem, VRP, TSP. This class of problems normally is no polynomial time. Okay, so that's why it is important to you when you are going to solve this type of problems, you need to have another tools. You cannot rely on mathematical programming. You cannot rely on exact solutions. Why? Because your problems belong to no polynomial time or NP. At least it is NP complete. For VRP, it's normally NP hard, right? So when you have this type of problems, you cannot rely on exact algorithms, especially when you are solving large size instances. For small size instances, it's still okay. Some algorithms still, exact algorithms still give you result and still even give you optimal solution that you can use to verify your approximation algorithms. Okay, then I talk about approximation algorithms. So what I mean with different tools here is we have exact solution approach, the one that you already studied, mathematical programming using solver. Inside the solver, we have the several exact approach like branch and bound, branch and price, column generations, Lagrange relaxation, right? But this one, because it is not applied for large size instances, you need to have another way. This one, we call it approximation algorithm. So instead of you find the absolute best or the optimal solution, you try to you satisfied with the approximation, or at least it's good, it's near best, it's already okay to me, and I can use it, and I can find it in a very, very reasonable time, right? Yeah, it's like when you reflect it to your real life. Some problems, it's so complex, right? It's so complex. you may not able to explore all the possibility to make sure that for this particular problem, you will find the best solution, because the possibility is so many and it's difficult to make sure whether this one is the best or not. Okay, so exact algorithm for those problem in your life will not give you, will not get you anywhere, because they are, these algorithms, too busy searching, right? No result, too many searching. But for this type of problem, perhaps you can try approximation algorithm. You can try, and then even though you know that I know this one is not the best, or I cannot guarantee this is the best, but with the good design of approximation algorithm, you can approximate so that it is close to, or it can approximate. That's why the name is approximate. It can approximate the exact result, even though you cannot make sure that is optimal. Okay, that's why this second type of algorithm exists. Okay, I guess that's enough for the complexity. Okay. Yeah, but yeah, still the rules is like, if the algorithm, the exact can be found, you should use that one, right? Yeah, because can be, there is an exact algorithm, but it cannot be applied for your problem. You can try approximation, but there is exact algorithm and it can apply for your problems. Then you still proposing approximation algorithm. People will ask, why do you use approximation? You can get the exact result, right? Okay, that's a how to say, that will be raise some question if you, if there is a known exact algorithm and can be used to, can be defined, can be applied to in a reasonable amount of time, then you don't use it, people will ask. Okay, before we go to this one, I think we stop and digest it for a while, and I will pause the recording. Meanwhile, I think it's already about more than 15 minutes. I think I will go back to master degree student. Let's discuss about your project. Yeah. The next part is about solution methods. Okay. So with the knowledge of the problem complexity that you already learned earlier, okay, we have two types, right? Algorithms complexity with the notation, big O notations. And then from those algorithms, you can check whether your problems is able to solve within polynomial time or not. If it is within polynomial time, you can consider it's P problem or polynomial problem. It's not difficult to solve. You just need to find the algorithms. But if it is not, you need to find, it is belong to NP. You still need to study which one is it, NP hard or NP complete. Then you can explore what type of algorithms normally used for that particular problems. Normally, it will belong to approximation methods, and it will not give you the optimal solution, but give you good enough solution for a reasonable amount of times. So that's why that is the importance of knowing what type of problems that you are handling or you are facing. Okay, then okay, this slide actually from my friend. He's a postdoc in Korea right now. I have the YouTube, but it's in Indonesian. We have a good discussion last month. He summarized very good what is the these two polarization, exact method and approximation method. What are the details of those methods? Okay, because it is a category as well. And then you can see from the perspective of solution quality, it means that how good is the solution that it can create or it can generate, exact or approximation. we can compare. And then we can also compare in terms of computational time, right? So the trade-off is like that, right? When you have a solutions that can solve in a very let's say optimal, the best one is optimal, right? Optimal solution give you optimal solution. But as you know, the problem sometimes belong to NP hard. So optimal solution tend to have longer computational time, and it sometimes very, very long, right? So that's the things that are discussed in this slide. Okay, first you see this one, the left part. There are several. There is mathematical model. We already learned about it, right? We have mathematical model formulate something in mathematical way, and then you can how to say it, why should you formulate in mathematical way? Because it is easier to deliver to many many people without introducing bias. Okay, if you use not mathematical model, just formal definition, just a sentence, sometimes it is bias involved. So people have different understanding about sentence. But if it is a formula defined in a formula in a mathematical way, the chance of bias understanding about something is very, very small, even non-existent. Okay. Mathematical models is solved using normally mathematical programmings. I already introduced to you the tools, so a lot of tools available. Even there is free, there is open source, there is proprietary, and each of them has their own pros and cons. But in general, we can say that mathematical model, mathematical formulation try to give you optimal solution, the best solution possible. But the trade-off is that if it is belong to NP hard problems or the problem complexity is high, the computational time will be longer. And normally mathematical model will introduce or will use exact method. So it may not appears directly to you, because normally the software that we are using is already hiding nicely the heavy workload of implementing exact method like branch and bound, branch and price, dynamic programming, Lagrange relaxations inside their software. So you don't have to see those difficult code. This is very difficult normally to code. You need to understand the mathematical property of it. And after that, each problem may have different approach for implementing it. But mostly it is hidden in your solver that we not commonly call as a solver. For example, last time we have AMPL is the mathematical programming language. And then AMPL can call several solver. For example, there is Gurobi, there is Simplex, there is Minos and stuff, and many. Those solver normally have embedded exact method inside of their implementation. Okay, so because these two is a pair, actually they are having the same characteristics. Try to find the best or the optimal solution, but with the trade-off of long computational time. Long it actually relative word, but as you can see previous example, you can approximate that with the TSP itself, the number, the approximation of the computational time is grow very, very high along with the increased number of the number of problem size. Okay, so this is exact method. Okay, exact method, these two. Okay, and then before I go to this one, this is the approximation method. Approximation. Okay, we have exact and approximation. Actually, we have this one, a more advanced topic. Okay, even though this class called advanced optimization, but we are not discussing this. Okay, simulation is in the AOT2. Okay, What is simulation? Normally, because this one is simplified the problem, right? Simplify the problem, make it deterministic. So we disregard several complex property that actually might be useful to be used to analyze the problem. So that's why you need to still learn AOT2 to let you have the skill to embed those many complex factor. And then sometimes it is more suitable if you want to have nice graphical illustration as well to about your problems. But of course, because you introduce more complex consideration, sometimes fine optimality is not an option, but you can find a good solution quality. And the computational time, it really depends on how large of your simulation. It will discuss in the next class, so I will not go deeper on that one. Okay. Another one is, okay, this approximation method, later I will discuss in more detail, actually now getting, how to say, more and more popularity, but they have the drawback of solution quality is not that. Sometimes we call it good, or sometimes we call it suboptimal, because we are not sure how good it is, but we are positive that is near optimal, suboptimal. Okay, so actually we are trying to closer the gap from suboptimal or from average or from good solution to as much as possible with close with the optimal. Okay, or in terms of computational time, sometimes it is also long time, even not as long as computational time of mathematical optimization. That's why the other way, we sometimes combine, okay, this one, advanced approach, normally integrated or combining what is a good property from exact solution with the good property of approximation solution. Okay, what is good from exact solution? The optimality, of course. Okay, the more optimal your result, the more confident you give the recommendation for the decision maker. But again, it is with the trade of computational time. Okay, so you try to see from the perspective of approximation solution. Actually, they can provide a good solution, but very fast. Okay, how can you improve this? How can you improve their solution quality to be near optimal, and at the same time it's okay to improve a little bit on the computational time. At least it's not as long as the mathematical or exact method. So there is the things called combination. Okay, combination can be between exact solution and approximation solution. It called normally math heuristic, mathematical and heuristic, math heuristic. Or sometimes they also combine between the approximation algorithm, because approximation algorithm also so many, they have their own drawbacks. So you have terminology called hybrid algorithm. For example, you have we will learn about PSO in next, particle swarm optimization. But other than PSO, you may already heard as well another meta heuristic algorithms such as genetic algorithms. Okay, PSO, tabu search, simulated annealing, variable neighborhood, iterated local search, ALNS, and even more and more meta-heuristic algorithm being introduced. So how do you choose? Sometimes it's another optimization problem, but there is a trend also combining good property of one meta-heuristic with another meta-heuristic, and hybrid those property, it becomes hybrid algorithms. That's another advanced integrated approach in solution method for optimization algorithm. Okay, and the one that I just I think it is getting more and more popular recently is we are going to integrate with the I think we can say that machine learning, artificial intelligence is one particular area that is really getting many people involved, and then they have like quite a good push on those uh, how to say uh, uh, advancement, push on the advancement. For example, why do I say like that? Now when you learn optimization, okay, you need to learn a lot of things, mathematical programmings, algorithms, and then optimizations. Compare it now, right now, not 10 years ago, but right now. Compare it when you learn data science, machine learning, artificial intelligence. See which one has more resource, which one is easier to enter. It means that, for example, when I first time start learn data mining way 6 years, 7 years ago, there is not many library like pandas, like numpy, like all those Python or R library available. It is available, but not as easy as right now. You just import and then you use the parameter, and then voila, you seems like you are a data scientist already. Some people like that, but actually you still need to know the basics. But in terms of entry point, that is very convenient. Compare now to if you want to learn optimization, how to say, how many stepping stone, the differences between entry to optimization compared to entry to machine learning. So many. I think when people ask to choose what do you want to learn nowadays, which one is easier, absolutely the answer in terms of newbie mostly will be machine learning or data science. Okay, but that's not bad. I mean, like, if you have one field or one area already advanced, we can we can try to embed those advancement to our own field. For example, if you are in the field of optimization, you can embed those because it's easy to enter. Then you can try and then see. Sometimes combination make things good, sometimes make it not good. Yeah, it depends. It is a research. Sometimes you find a good result, sometimes you find a bad result, but that's the nature of research. So, but somehow what I saw in the trend, okay, if you read several papers, there is getting more and more people integrate their field with machine learning, artificial intelligence. That's why it is also here, embedded here. And then I think if you are going to pursue this path, you should also consider about that. Okay, those are the two part here. Okay, where is it? Here and then here. Okay, now I will focus my last chapter or last the following class discussing about this, because this one already done. I think I have already give you a brief explanation, implementation. Even I hope you already be able to use those several tools that I introduced. And then this one will be discussed in another class, so it's not here. I left that to the other lecturer. Now my responsibility is, I'm not sure you will be able to grasp it in like 3 to 4 weeks, but at least I hope I can give you a good introduction. Then you can explore it by yourself later. Okay. Okay. Now let's talk about approximation algorithm. Approximation algorithms, in terms of solution quality, they can promise you good solution, or at least average here mentioned. Okay, and it is very, very short amount of time even, or at least average, not as long as this one. Okay. Okay. In the early days of approximation algorithms, we have algorithms called that, or belong to rule-based and heuristic algorithm. Okay, actually this one is have some intersection, some intersect one to another, but basically sometimes we call rule-based also a heuristic algorithm. Okay, sometimes heuristic, most of the heuristic also belong to rule-based. Okay, okay, that one point you need to take care. So this one sometimes belong to one category called heuristic algorithm. And then start from the advancement of computational power. What does it mean? When people start to have their own ability to produce those computing power, it means that when they start to have their own PC, it is most easily available. People start to embrace that and then come up with the how to make these heuristics able to get a better result. Okay, so it is somehow an improvement, we can call it, from the rule-based and heuristics. But improvement doesn't mean that they are get rid of these two category. No, they are not replacement. Okay, meta heuristic is not a replacement for heuristics. Okay, meta heuristic, if you study the history of meta heuristic, or if you later, I will later introduce you to the concept, we can say that meta heuristics is here actually to improve the result of heuristics. Okay, this one is heuristic, this one is meta heuristic. Meta heuristics is here or appear or introduced actually to improve the heuristics. So they are not the replacement. Okay, so whenever you see that, why sometimes I see there is heuristic inside meta heuristics. Yeah, it is supposed to be like that, because meta heuristic is more to an improvement algorithms. It's more to exploration algorithm to find a better solution for compared to the previous solution. And heuristics is more to like construction algorithms. So you build a new solutions from zero, from no solution to one, or there is a solution. And meta heuristics is from one to many. I mean, like from one solution that perhaps already good or at least average using heuristic or rule-based, you try to improve it, make it better. That one is the task of meta-heuristic. Okay, I hope that one give you a clear explanation about heuristic and meta-heuristics. And of course, you can read again the theory. Maybe if my wording is not really good, you can rely on the good and proper and better divine wording from the books. But I hope the concept, I think the concept is already there, as I mentioned. So it's like what I said, but the wording maybe misplaced one or two, something like that. But again, check again with the books. Okay, that is one. Okay, this is now we if you talk about rule-based and meta-heuristic, this rule-based and heuristic. Okay, so today I will discuss this one first. Okay, hopefully we can at least give you one example, and then next week we start with this one. Okay, okay, so rule-based and heuristics. Okay, their characteristic is really how to say, we can say that problem dependent. What does it mean, problem dependence? Okay, first, rule base. Rule base is clear. It's the name explains itself. Rule base, when you have a problem, you make a rule to give the solution. Okay, for example, you have a scheduling problem. I want to schedule my machine. I have 10 jobs. Each job has it has its due date. You create a rules. Each job has due date, processing time, and then perhaps due date. Yeah, that one, just do first. Due date, processing time, or maybe release date. The first time it's come, when the job is appear. Release date, due date, and then processing time. Simple rule. How do you schedule the job? Which one you will do first for your machine? Let's say you have one machine. Then for this type of solution, there is a rule base, very famous. First come, first serve. That is rule base. Which job coming first, you serve that one first. That is rule base. Okay. It is an algorithm, right? Algorithm is a step by step of doing something. They have input, they have output, they have process. The process is defined by the algorithm. Okay. Okay. We go back to rule base. Shortest processing time. There is another rule base. First come, first serve. Shortest processing time. Okay. What's the difference? One, consider if the job already available, you should process it. But the other one, consider that why don't we process the fastest one first so we can deliver more, something like perhaps like that. Which one is better? It depends. Depends what you need, what's your objective. Okay, you need to explore more. Which one will be better for what kind of objective? There is the theory in the scheduling theory. Another one is earliest due date. Okay, if you don't want to have many late job, you try to solve the one that have earliest due date. It's like when you do homework, for example, you have many class give you homework. Which class give you the earliest due date? That one you will do first. Sometimes you do that, right? That is another scheduling strategy. Okay, and all those strategies belong to rule base. The question is now, is that applied only for scheduling or can apply to another problem? Okay, most likely, if it is still belong to the same type of problem, for example, machine scheduling, and then you compare to, like, say, staff scheduling, or let's say that one, homework scheduling, the rules can be interchangeable with small modification. But when you move to another problems that is not actually related, for example, scheduling problem, the rule base you use to create solution for location problem, for example, covering center problem, P median problems, it will not apply. So it is really, we can say it roughly, it is below, it will be related to the problem, closely related to the problem. So whenever you want to use rule base, okay, now the key points that need to be taken. Rule base is found, it is have its place in the society because easy to understand, easy to apply, and then very flexible for your problem, for your particular problem. So it is have popularity. Okay, so many people using it. But as you can see earlier, rule based doesn't guarantee that your solution is good. It is often average. Okay, it is often average, but it is feasible, and then it can be used. That is the sometimes most important in the practice. I don't care how good it is, as long as it works, we can use it sometimes like that. Okay, but as an optimization people as industrial engineering, industrial management, or business management, we try to improve. We try to, if there is a better ways, we try to explore that, right? So that's why there is another category like heuristics that try to improve from the rule base to make it better, or later on you have meta heuristics here, meta heuristics. And most likely, okay, heuristic maybe still really depend on the problems, but most likely meta heuristics like SA, GA, PSO, tabu search, and so on, they are independent to the problem. For example, you can use PSO for covering problem, center problem, scheduling problem, for TSP. Why does it like that? Later you will learn about this. The independency is high. So that's why when previously I discussed with Arvin, for parameter settings, it's also possible. Use the same meta heuristics. It is it's like Swiss knife tools, can be used for many type of optimization problems. Okay, but today let's discuss on this one. Okay, it is also limited time, so I cannot discuss on more detail. So I just decide to use this one first. Perhaps this one will be useful for your final project, in which we will discuss covering and center problem. Perhaps covering first, maximum covering, and then we will discuss something called greedy algorithms. Okay. Okay, to give you the basic foundation again, so that you are not forgetting what we are discussing earlier, and we can like have this discussion about what we are doing. I need to go back to the problem again, because it really depends on the problem, right? Problem dependence, rule based. Here we want to explore how the maximum covering location models being solved. Previously, we used exact solution. Just plot this one to optimization solver, mathematical programming, then you can get the result, right? And I think we do that for the homework also already. So it's nicely done, and it is give you a very, very good result. However, we only tried for small sample. Yeah, if you remember this one, yeah, this is the one of the way we can do it. You need to make it like this if you want to become Excel, but if you use ample, you don't have to really break down to like this. You can, sorry, let me drink first a little bit. Okay. You can directly solve from the mathematical model like this using ample. Okay. Yeah. For this one, I hope you already still remember. What we are going to find is the minimum, not minimum, maximum this one. The title is maximum demand covered. Okay, let's say you have limited budget to assign the capacity. You can you to assign the facility. You only able to build one facility, and the distance coverage is 11. How do you decide among this facility, candidate facility A, B, C, D, E, F? Which one should you assign? Okay, if you have only one possible facility to be assigned, you can use this formulation, and then later on you can experiment. What if we can assign two? What will be the difference result? Something like that. That's why you need to model it as a mathematical model. But for some paper, some researcher mentioned that if you make the number of the location facility quite large, yeah, the option is quite large, and then you sometimes modify a little bit on the constraint, this problem will belong to NP complete. Okay, now we have the same understanding of hopefully already about NP complete. NP complete, it means what? It means that your problems for some instances might be difficult to solve. Okay, so you have to find another way other than mathematical programming to solve this one. Okay, that's why first we want to try the rule base. We have several, right? We have okay, we have rule based, heuristic, meta heuristic. Let's start from the easiest one, rule based, which is called greedy adding algorithms. Okay, what is greedy adding algorithms? Okay, let's go back here. Okay. Okay. Greedy, okay. Greedy means that you are always trying to get the best solution at each iteration. Okay, you are greedy. Okay, for this one, the decision is what? The decision is to select which facility you are going to use or you are going to establish. Okay, since you are greedy, now you are going to see if I only have to choose, if I can only choose one facility, if you are greedy, what should you do? Okay, now the logical way is I need to know what is the objective first, right? Okay, that's why you find my objective is to find the maximum covering. It means what is maximum covering? Maximum demand it can cover if we use a particular facility. Previously, we have 6, A until F. We check one by one. If I can only have one facility to be used, which one cover the most? That's where I will establish my facility. It's common sense, right? Yeah, rule-based is basically common sense. Okay, so based on this one, okay, based on these ideas, okay, if one facility I choose the most, the one that cover the most demand, okay. Now the question is, what if you get another opportunity? You can choose two. How do you select now? Okay, how do you select? Okay. Now, if we go back, now it is an algorithm. It is a rules that you create. Okay, I am consistent with my rules. If I have more chance to add the facility that I can use, I will be still greedy. Okay. So the first one, I will check how many facility, which facility cover the most. Okay, I establish that one first. And then I rule out the one that already covered by those facility. In the second iteration, if you want me to choose again, I just choose again which one get the most cover among the rest that is not yet being covered, right? That is greedy. That is how greedy works. Okay. Okay. Now, if okay, that is the oral explanation, right? And again, when you explain something, if you use oral representation, sometimes there is a bias on the understanding. That's why we are often use this type of way. Either we use flowchart or pseudocode to explain how things work, how step by step we are doing the one that we already explained earlier. Okay. And I think if you are developing algorithm, if you are using algorithms, you should able to define the flowchart like this. This is another skill you need to understand. Okay, and each flowchart has its symbol. For example, this symbol here, it is the start and the finish of the flowchart of the algorithms. And square, it means that this is a statement or a something that you need to do. Okay, and this one also square, square, and then this one is how do we call this shape? Uh, how do we call it this shape? Okay, this shape lah. I suddenly lost in translation. Okay, this to represent decision. Okay, when you have this symbol or shape, you will get branches. Okay, for example, here you have this symbol. If the statement inside of this symbol say yes, you will go here. If no, you will go to the other direction. Okay. Okay. So there is 3 symbol you can you are being introduced here. There is more to it, but I think it is enough for us to explain this algorithm. Okay. Go back to the explanation that I mentioned earlier. How greedy works. Okay. Find the most find the facility that cover the most demand, and then choose that facility and then update, right, for the next iteration. That's the if you can still choose, update the demand, update the condition, and then choose again the same way, the same approach. Okay, to formalize that, this is the way. First, this is still listen. Okay, this still oral, still in simple sentence. First, you need to find the candidate side that cover the most uncovered demand. How do we translate this one into code? Later, you will see. Okay, but this is the idea. Second, locate the next facility at that site. Okay. Third, remove all the demand covered by the current condition. So later on, if you can still choose, you go here. You still cannot choose, that's the solution that you found. If you can still choose, you do the same thing again. Okay. It is easier to see the example along with this flowchart to make it easier to grasp and understood. Let's say we use the same example that we have earlier. Okay. Sorry, this one should be 11. Why is it 9? Okay. Okay. We have maximum covering location problems. We have the data. We have 6 facility that be candidate facility that is as well as customer facility. Each customer has its demand. Okay. And to represent it, we have the distance constraint. This one I think should be 9, or this one 11. Okay, let's see, either 9 or 11. It means that you will consider one, if you open, let's say A, and then you will consider A will cover B if it is less than this coverage distance. Okay. Okay, we have those coverage distance data later need to be processed. And then if you want to find this solution, we need another parameter, which is how many facility you can open. In this case, let's say we have 3 to see how we can iterate on this one. Okay. Okay, let's start using this example. First, the first step in greedy adding is number 1. Here, I put red box here. This is the enlarge of the explanation. Find the candidate that cover most uncovered demand. To do that, what should you do? Of course, first you need to list all the facility that is available, that is not yet selected. For the first iteration, all is not yet selected. And then you need to check. If you open the facility in A, okay, A here, A will cover which one? Okay, it's 9. A, you check what connection A have, A to B, A to C, A to D. But wait, A to B, so it's 11 actually. No, it's 9. Sorry. 9. A to B, A to C, A to D. Okay. Now you check among this connection, which one is less, the distance from one point to another point is less than 9, less than coverage distance. Those nodes we consider as covered. Okay, the first one, of course, A itself, because A to A is 0, no distance there. If you open in A, of course you will cover A, so you put A here. Okay, and then you check A to B. Okay, the cover distance is 9. 9 is greater than A. It means that B can be covered from A if we know that the cover distance is 9. So B is covered. And then what about C? C is 15. 15 is greater than 9. So we don't consider C is covered from A. So we don't put C here. No, cannot. And then the last one is D is 10. 10 is greater than 9. So D is not covered from A. So you don't put A here. Okay, you have now. What about E and F? Of course, you can find the shortest path, but from this one, we already see that if until D already 10, you cannot grasp any this one 16. There is no way you can approach E and F less than 9. Okay, so A, B only. Then if you open A, what does it mean? If you open A, you can cover demand from A and B. So it means that demand in A is 10 plus demand in B is 8. The total is 18. So those are the total demand that you can cover given you open candidate facility in A. Okay, we populate the same way for all the candidate facility. Okay, then you can see all the total demand covered. Here, the rules. What is the rules? Find candidate site. Okay, you already check all the candidate site. Cover most uncovered demand. For the first time, all the demand is uncovered. So it means that if you want to open for the first time, you, based on this rule, we select F, in which the total demand is 55. Okay, so the first step is selecting finding F. So you find among all, and then you find F is the answer, and then you move to the next step. Okay, I know F is the best for current iteration, so I decide to select or locate the facility at F. So I put yellow highlight here. So it means that F is open. When you decide to open F, then you go to the next step. You need to consider F is already F and its connection. Okay, F and its connection. What is the connection with F? Oh no, only F. So F and its connection mean only F will be removed. Remove all demands covered by the most recent cited. Okay, remove all the connection with F. So we take out F here. You can see F is missing from here. And then you update the total demand. Okay, the connection still in place, but the total demand maybe not. But for this one, because we only delete one row, so the other one doesn't really affect it. Okay, now we go to the fourth step. Fourth step is what? It's a decision. Okay, you need to check, have P number of site. Okay, we have P equals to 3. Now we have P equals to 1. Okay, we only open 1. we don't open more than one yet, is P number offset has been located. Are we using all our quota already? Of course, the answer is no, not yet. Only one yet. Only one we do. The other option is, okay, but if you not yet use 3, but all your demand already covered, so that's the optimal one already, right? All the customer demand already covered, so you don't have to continue. So here the algorithm also asking for, first, if it is you already finished 3, you already assigned 3 facility, or if all the demand already covered, so you will this one 0 1, this one is OR, right? Or is this one 0 1 1 0 1 1 0 0. This will be equals to true if one of them equals to true, right? 1 represent true, 0 equal false. So when does it go up? If you are not yet opening 3 facility and the demand, not all the demand is yet being covered. Okay, so here you can see this is the demand that we need to cover. There is still a lot of it. And then can we still open the facility? Yes, we still have two still can open. So what should we do? Yeah, we just need to find more facility. Okay, so you go here, find more facility, you go to back to the first iteration. Okay, yeah, following the algorithm, so you go up and then go to the first box again, which is find candidate site that cover most uncovered demand. Okay, how do we do it? Same way, but now we don't consider F because F already being selected. Okay, now we have only A, B, C, D, E. You have here A 18, 36, 29, 26, 29. So this will be the facility that you are going to select. Okay, I find it. I find the facility that have the most uncovered demand. It is B. Okay, then what? Then locate that facility. You will use that facility. So it means you will use B. B will cover A and D. Okay, A, B, D. Then what? Then next, you need to remove all the demand covered by the most recent cited facility. It means that B is connecting A and D. So you need to delete B, A, and D. So what is it left? C and E. Okay. C and E. This one and this one. Okay. And then you already remove it. Okay. Next, go to the fourth step again. You need to decide the same question. How many facility you already open? P open is 2. You only have, you still have one more to open, 3. Okay, so the first one, P site have been located. No, not yet. We just open 2. We still have one more. And then the second question, are all demand covered? Also no. We still have this one, C with 29 because 22 and E because they cover each other. E also cover each other, 22, 29, 29. So what should we do? Go back again to the first initial solution, first box. Find again, find one more at least. Okay, then you go. Okay, now here we have this 129, this 129. What should we do? Well, if you check the property, it's equal. They say cover each other. So if that's the case, you don't have to worry. Just pick any, because it has the same solution. Whether you open C or open E, it gives you the same result. Okay. it gives you the same result. It means here, let's say we open C, and then we locate C, and then next we delete all the demands. For this one, if you go to the fourth one, actually both of them is satisfied. You already open 3 facility, all the demand already covered. So finish. Yeah. I think this one is not or, should be. Let's find out again later. But at least like this, if you already open 3, you cannot actually you cannot open more, right? Even though, because we don't have the restriction to cover all the demand. But that's okay. I hope that gives you a good introduction about greedy algorithms. Well, actually, I have prepared for the coding section, but I'm afraid that it is too late already. So I'm thinking that we can do this one next week, or I'm not sure if I can make video. I can make video for you so you can learn by yourself first. Next week we just try to implement it. But I think I will leave this to you to give me suggestion. What should we do? Should we code next week? But for this week, I'm not really recommend for continuing to coding right now, because it's too yeah, it's a little bit late already. It's time to have lunch and things. I think you need to refresh first and grasp the idea of this greedy algorithm as well. Okay. Up until this, do you have any questions? Okay. The code is here. You just need to open it. Let's say, let me try. No, why I cannot? Okay. Okay. Here you go. Yeah, if you open that link, you will find this code. I already give you this. This is the data. It is exactly the data with the same data with the example. You can see the code to understand what is this, what is that. Basically, this one is the number of facility, number of customer, number of P, number of facility going to be open. This is distance. This is the demand. This is the name of the facility, and this is the travel distance. Okay. But later I will explain again. You just need to open this. You can normally it will automatically copy it to your. This is a how to say, online IDE, so you can code it online. You don't have to install anything. Just create account here and then open this link. It will automatically copy it to your browser or account. Then you just need to run, and you can get the result of the code here. I will explain to you how does it works, but this one is in C#. So if you have time, please see the programming language using C# first. If you don't understand, that's fine. If you don't want to continue to use this one, that's fine. Later I will try to give you another version if possible, if my time is if I have time to do that. Here, what I can do is like this. From this data, okay, they read the data from the file here. So you can just easily change the file, and then you don't need to change the code. You will get this one if you decide to open 3 facility, right? So the one that being open is B and C and F, exactly what we have with the algorithms that I show you in the PowerPoint. How does it work? It basically implement all those how to say, all those flowchart. You can see step 1 find, step 2 locate, step 3 remove, step 4 check, repeat. That's it. But each of these has their own has its own how to say, has its own implementation. How do we calculate total demand coverage? There is a function I create for that. I will explain it in detail next week. But normally I'm not using this for coding because for research purpose, it's difficult to use online IDE. This is suitable for teaching, but for research purpose, normally I use this one, Visual Studio. It is more complete IDE. Has many powerful tools like debugging tools, application development tools and stuff. It is community based, so it's free, but it's enough to do research. Many of my paper I use this IDE, but again, you may need a different set of tools. It depends on you. For example, if you use Python, you may not use this one, even though this IDE can use for Python as well. Python may be the most popular one is PyCharm, or I think there is another light version of this one, like Visual Studio Code, or you can use the Anaconda package they provide with Jupyter Notebook, Spider, and stuff. They're also possible to be used, or even you just use text editor like Notepad. That also possible to code using Python, or even C# also possible, but it is a little bit more difficult to maintain. Okay, this one, let's discuss it next week. Hopefully we can have more time to discuss about it. For now, this is what I can deliver to you. There is another improvement of those greedy algorithms. This will lead you to the heuristic algorithms. And then that heuristic later on we will discuss as a this is much more complex. You see, this is the basic one. They have improvement here. Substitution algorithm have another flowchart to do. This one we will implement also. At least I can give you the code for implementing this substitution algorithm. It can significantly improve from average solution to a much better solution. Okay, I think that one for this week. I hope you are doing well. For master degree student, please submit the midterm also. You have one more week to do that, and also find the data for your project ideas. I think those two projects that you already discussed today, I think it's a very great. At least it can be published in conference, Scopus Index conference. I'm not sure whether it will be beneficial for you, but I think it is always good to have additional portfolio or additional achievement. We can say it's achievement from our class. We are not just learning things, but we have a proof that we already able to implement what we learn here and then show it to the world. Doesn't matter it is how to say, it is very impactful or even just slightly impactful, but the topic, I think it's good. It will be interesting to be discussed with the college, with peers. Perhaps you can open more opportunity from there. Okay, and yeah, I think that's for today. Before I close, do you have any question?